If we have a frame with non-prismatic members, that is, members without a constant cross-section, the moment distribution method is still applicable, but the bending stiffness and carryover factors must be calculated for that unique member or set of members. So in this problem, we're going to find the bending stiffness and carryover factors for non-prismatic members. The key concepts we'll cover are using superposition to represent loading and reactions for an indeterminate beam, and using the conjugate beam method to develop equations for displacement and rotation. And here's our non-prismatic member. For moment distribution, this might be one member in a much larger frame, or one segment of a much larger indeterminate beam. But since we're focusing on developing the properties, we're going to just concentrate on this one beam. We're going to determine the stiffness for node A for the beam and the carryover factor, how much moment carries over from node A to node C for this beam. The beam starts out with fixed supports at A and C. The moment of inertia is provided for the two parts of this beam, and the modulus elasticity is that of steel, 29,000 KSI. And here's the approach we'll follow. We'll start by approximating the answer. In this case, part of the answer will bound, part of it will approximate. Then we need to represent the beam in such a way that we can calculate the stiffness and the carryover factor. We're going to identify the moments that we would need to superimpose to represent the behavior on that beam, or to represent the internal moment generated in that beam. Then we're going to create the conjugate beam with the m over EI as loading. We'll apply equilibrium to the conjugate beam. And then we will have sufficient information to find the stiffness and carryover. We'll wrap up by comparing with our approximation. Now step 1. Let's approximate the answer. We do that so that once we've completed our calculations, we have something to help us judge whether we have a reasonable result or not. So let's start by talking about bending stiffness. Our beam has two different moments of inertia, but what if it was prismatic? It was made only of the smaller moment of inertia. Well, then the bending stiffness, AC, would be 4EI over L, because the member is fixed in its idealization. So we have 4 times the 29,000 ksi, the 600 inches to the 4th for I, over the entire length, which is 27 feet. We have mixed units. Let's make the numerator feet instead of inches. We have inches to the 4th over inches squared, so the numerator is kip inches squared, and so we'll square our conversion. Put these together, we get a bending stiffness of 17,900 foot kips for member AC. Well, what if we went to the other extreme? What if it was all made out of the larger moment of inertia? 900 inches to the 4th for the entire beam. Well, then the bending stiffness with a larger moment of inertia increases, all other things being held the same. So with 900 inches to the 4th, we still have our unit conversion, still 27 feet long. Then the bending stiffness becomes 26,850 foot kips. Well, reality is somewhere between. Part of the beam has the smaller moment of inertia, part of the beam has the larger moment of inertia. So when we're all done, we'll expect our answer for the bending stiffness, K, to be somewhere between these two extremes. Now how about the carryover factor? Well, if the beam was prismatic, then the carryover factor from A to C, that is, when I release moment into end A, how much of that moment carries over to end C, is a half. Well, since it's not prismatic, we're going to expect that to change, but I wouldn't expect it to change substantially. Certainly not 0 or 1. So we know we've bound the answer between 0 and 1, and it'll probably be something close to 0.5. Now step 2. To find the bending stiffness, we need to represent the beam differently than fixed. To find the bending stiffness, we need to take our beam and switch the fixed support at end A to a roller support, because bending stiffness is the moment required to cause the end to rotate 1 radian. So when I apply moment, we'll call it MA, to this structure with the different moments of inertia partway through, we draw our elastic curve, our deflected shape. We're looking for the moment required to give us exactly 1 radian of rotation or slope at that end. And I'll point out this is a negative rotation, so let's call this -1 radians. And then we're also looking for the moment created at the other side when MA is applied, and we'll identify it by the carryover factor times that moment. So there is a moment generated here, and we'll express it as the moment at the left and whatever carryover factor is required to convert this moment to convert this moment to the combination we would calculate here. And now I'm ready for step 3. Superposition of moments. The conjugate beam method requires that we construct the M over EI diagram for this beam. And to do that, I'm going to superimpose two situations, or two moment diagrams. So what we have is this. But to create that, I'm going to use a determinate beam so that I know how to construct the moment diagram. With the moment at the left end applied, and then another beam with just the moment applied at the right end. Well, the moment diagram for our first case starts out at MA and drops linearly to 0 at 27 feet. And I know it has to be linear because there's no distributed load, so the shear diagram must be constant, and if the shear diagram is constant, the moment diagram must be linear. I know it starts with the positive jump of MA, I know it has to be 0 at this pinned end, and so it decreases as such. I also know that out here, 12 feet across, I'm going to want to know the moment. And so if I use similar triangles, I have 15 feet here, 27 feet here. This value of moment is 0.555 times MA. Now the moment for this situation, or moment diagram for this situation. In this case, the moment starts at 0. We can see again that it's linear, and the shape it will take is concave down, so it's a negative moment. Not to be confused with clockwise is positive all the time. In this case, we're talking about internal force diagrams, and so concave down means negative moment. And so at the 27-foot mark, we have the peak negative moment, which is the distribution factor times MA. And at that point of 12 feet, again using similar triangles, we have 0.444, the distribution factor, times MA. Now step 4. Creating the conjugate beam. To do that, however, I need to convert our moment diagrams from the previous slide to M over EI for the beam. And it needs to reflect that I is different from A to B and from B to C. And I'll draw both of those moment diagrams on the same figure here. This side being positive moment, this side being negative moment. So we saw on the positive side, we start with MA over 600 inches to the fourth E. And it decreases until 12 feet to 0.555 times the moment at the left end, and the moment of inertia is still 600 inches to the fourth times E. But then once I cross over to the right side of point B, so this is at 12 feet, and so just to the right of point B, the moment of inertia changes, it increases, so my m over EI quantity drops to 0.555 times the moment at the left end A divided by 900 inches to the fourth E. And from here it decreases linearly to 0 at 27 feet. Now on the negative side, we started at 0 and decrease linearly to the magnitude 0.444 carryover factor times the moment at the left end, and that whole segment has a moment of inertia of 600 inches to the fourth and then times E. As we cross over to the right, the magnitude drops, and so we have 0.444 carryover factor, moment from the left end, the 900 inches to the fourth E, and then it increases in a negative moment linearly till we reach the 27 feet, and its carryover factor, moment at the left end, divided by the 900 inches to the fourth E. So now we have the M over EI diagram, which will provide the loading for our conjugate beam, but we need to construct the conjugate beam itself. So I'll draw a beam, and to do this we need to go to Table 8-2 from our text. Table 8-2 shows us how to take aspects of the real beam and convert them to how the conjugate beam should look. So we need to go back to our representation of the beam, and we see that the left end is pinned, or a roller rather, and the right end is fixed. So if the real beam has a roller at one end, the conjugate beam has a roller at that end. If the real beam is fixed at an end, the conjugate beam is free at that end. So our conjugate beam looks like this. Roller on one end, completely free on the other. Now normally this would look indeterminate, or not indeterminate rather, but unstable. But in the conjugate beam method, the loading we apply will keep this structure in equilibrium. So let's draw the distributed loading on the conjugate beam. And this distributed loading has an interesting shape, kind of a trapezoidal section and a triangular distributed load, Here a triangular distributed load and then a trapezoidal distributed load. So we're going to convert these distributed loads to equivalent forces acting at the appropriate place. And so I'm going to take this distributed load and divide it into regions. So that I have a triangular region, a rectangular region, a triangular region, a triangular region, a rectangular region, and a triangular region. And so the equivalent force or resultant force acting on the conjugate beam due to this triangular region I'll call force 1, and it acts at a resultant 1/3 from the end. My resultant due to the rectangular distributed m over EI loading we'll call force 2, and it acts at the center or mid width of this rectangle. Force 3, and then those below the conjugate beam are coming from the negative m over EI diagram, and so they act downward. Force 4, force 5, and force 6. And now let's label the locations. This force is 1/3 of 12, so this one is at 4 feet. This one is half of 12 at 6, so that's 2 more feet. And we have 6 feet. And then if we look at this triangular region, it's 15 feet long. 1/3 of that distance will be 5 feet, which leaves us with 10 feet on this side. And down here, again, this is 12 feet, only now we need 2/3 of it, so it's 8 feet from A to force 4, then another 4 feet, then halfway across the 15 feet is 7.5 feet. Force 6 is 5 feet from the end, which means there is 2.5 feet here, and then 5 feet to the end. So let's calculate these force resultants. Force 1 is triangular, and so it's 1/2 times, and we need this height, so it's this quantity minus that quantity, MA over the 600 inches to the 4th E minus 0.555 MA over 600 inches to the 4th E. That's the height of our triangular region, and the width of our triangular region, 12 feet, and that gives me a 2.67 feet times MA over the 600 inches to the 4th E. Now force 2. It's a rectangular region, so we just need the height, which is 0.555 MA over 600 inches to the fourth times E times the width, 12 feet. Put those together and we get 6.66 feet times MA over 600 inches to the fourth E. Force 3. This one. It's triangular, so we have 1/2. The height of the triangle we said is the 0.555 MA over the larger moment of inertia, 900 inches to the fourth E, and that is 15 feet wide. So we get 4.16 feet times MA over the 900 inches to the fourth E. Force 4. This triangular one. We have 1/2. The height is 0.444 times the carryover factor times the moment at end A, and that's divided by the 600 inches to the fourth E, and it is a 12-foot wide triangular distributed M over EI load. Put those together and we get 2.66 feet times the carryover factor times the moment at A divided by the 600 inches to the fourth E. Now load 5, or force 5. It's rectangular, so we just need the height, but the height is 0.444 carryover moment divided by the larger moment of inertia. And that's times a width of 15 feet. Put those together and we get 6.66 feet carryover factor, the moment at A, divided by 900 inches to the fourth E. One left. Force 6. This one's triangular, and its height we have to obtain by subtracting this quantity from this quantity. So you have the carryover times the moment divided by 900 inches to the fourth E minus the 0.444 carryover factor, moment at A, divided by the 900 inches to the fourth E for this segment, and it is 15 feet long. Put those all together and we get 4.17 feet carryover factor times the moment at A divided by the 900 inches to the fourth times E. And step 5. Now it's time to apply equilibrium to the conjugate beam. here's what's going to help us out in this process. Since the slope at A is -1 radian, the shear at A in the conjugate beam, which is also therefore the vertical reaction at A, has to be -1. And I said even though it looks unstable, the conjugate beam must be in vertical equilibrium. So we're going to write the equation of vertical equilibrium. Then we're going to need one more equation of equilibrium, which will be moment equilibrium, and we'll be able to solve for our two unknowns, the moment at A in the beam with the pinned end, fixed end, and the carryover factor. So let's redraw our conjugate beam. We know that the shear in the beam, in the conjugate beam at A, therefore the vertical reaction is -1. And we have 1/3 of the way across the 12 feet was force 1. Halfway across it was force 2. 1/3 of the way across BC was force 3, all of those acting up. 2/3 across A to B acting down is force 4. Halfway across from B to C was force 5. And 2/3 the way across from B to C acting down was force 6. So let's apply horizontal equilibrium, not horizontal, vertical equilibrium in the conjugate beam, or for the conjugate beam. We'll choose up to be positive, that prime representing the conjugate beam. So we have the -1 here. We need to add force 1, force 2, and force 3, and we subtract force 4, force 5, and force 6. So we have -1 plus, if we look back, these are all the quantities we calculated, and so I will write them in here. We had the 2.67 feet times the moment at A divided by the 600 inches to the 4th E plus 6.66 feet moment at A over the 600 inches to the 4th E plus 4.16 feet moment at A over 900 inches to the 4th E, and we subtract now force 4, the minus 2.66 feet carryover factor moment at A over the 600 inches to the 4th E minus 6.66 feet, the carryover factor, moment at A, over 900 inches to the fourth E, minus the last one, 4.17 feet, carryover factor, times the moment at A, over 900 inches to the fourth E. All of those have to equal 0. Now if I consolidate these terms and then these terms, I get minus 1 plus 18.12 feet times MA over 900 inches to the fourth times E. And so to combine these, I had to multiply each of these two by 1.5 so that I could get the denominators 900 inches to the fourth as well. So the numerators were each amplified by 1.5. Likewise for this one, so that it's the same denominator as these, and we get a minus 14.82 feet, the carryover factor, the moment at A, divided by 900 inches to the fourth E equals 0. And I'm going to call this equation 1. Although the conjugate beam looks unstable, with the applied loads, the conjugate beam must be in moment equilibrium. So that will provide our second equation. Let's sum moments about point A. I'll use the prime here because we are summing moments for the conjugate beam. We have force 1 acting through 4 feet. That's a positive contribution. We have force 2 acting through 6 feet. It's a positive contribution. Force 3 acting through 1/3 of the 15 plus the 12. And that's a positive contribution. We have negative contributions from force 4 acting through 8 feet, negative contribution for force 5. We have 12 plus half of the 15, and a negative contribution from force 6, the 12 plus 2/3, which is 10 feet. So let's substitute in the values we have for the different forces. We have 0 equals, and if I multiply by the various lengths, I get 10.68 feet squared MA over 600 inches to the fourth E. And this force times the 6 feet, we add 39.96 feet squared MA over 600 inches to the fourth E. This one times 17 feet, we add 70.72 feet squared, the moment at A, over 900 inches to the fourth times E. Now, force 4 times 8 feet, we subtract 21.28 feet squared, carryover factor, times the moment at A, divided by 600 inches to the fourth E. And we subtract force 5 times the 19.5 feet, which is 129.87 feet squared, carryover factor, moment at A, divided by the 900 inches to the fourth times E, and our last term, force 6 times the 22 feet, and that is 91.74 feet squared, carryover factor, moment at A, divided by 900 inches to the fourth times E. Well, if I consolidate these terms, and remember to do so, I'll have to change the denominator to 900 inches to the fourth. So I'll amplify each of the numerators here by 1.5. And if I consolidate these terms, again needing to convert this one, we get 0 equals 146.68 feet squared, moment at A, over 900 inches to the fourth E, minus 253.53 feet squared, carryover factor, moment at A, over 900 inches to the fourth E. And that is our second equation. So now we're ready for step 6. Let's find the bending stiffness and the carryover factor. And to do that, let's start with equation 2. If we look at it, MA, or the units feet squared, MA, the 900 inches to the fourth, and E, is common to each of these two. And so if we multiply those out times the 0, we get 0 equals 146.68 minus 253.53 times the carryover factor. So if I solve for the carryover factor, we get 0.579. Now let's substitute the carryover factor into equation 1. And equation 1 looked like this. So we have -1 plus 18.12 feet times the moment at A divided by 900 inches to the fourth E minus 14.82 feet times the carryover factor, which we just calculated to be 5.579 times the moment at A, divided by 900 inches to the fourth times E. And that all equals 0. So if I combine these two terms, move the 1 to the other side, I get 9.54 feet MA over 900 inches to the 4th E equals 1. So MA must be 900 inches to the 4th E over 9.54 feet. And now let's put in for E and get our units consistent. So we have 900 inches to the 4th times 29,000 KSI. Let's make the numerator units of feet. We have inches to the 4th divided by inches squared, so we have inches squared left. We need to square our conversion and divide by 9.54 feet, and we get 19,000 foot kips. And that is our bending stiffness K for member AC. Now step 7. Let's compare with our approximation. We said that the bending stiffness would have to be between 17,900 and 26,850 foot kips. And as we look at the value we calculated, it is in between those, so that checks. For the carryover factor, if it had been a prismatic member, we said that the carryover factor would be 1/2. What we actually calculated was 0.579. So there is a difference, but it's not significantly different. It's certainly not order of magnitude different, and our carryover factor is between 0 and 1. So that one checks. So we can reasonably conclude that we have calculated the bending stiffness and carryover factor for this beam with the two different moments of inertia. Now let's go back and review the process we followed to obtain these results. We started by approximating the answer, and for bending stiffness we calculated the stiffness for a prismatic member with the smaller moment of inertia. We recalculated it with the larger moment of inertia, and we recognized that the actual bending stiffness of the non-prismatic member must be between those two values. For the carryover factor, we looked at the carryover factor for a prismatic member, which is 1/2, and said that the carryover factor in this case should not be radically different, has to be bigger than 0, and should be less than 1. We then drew a representation of the beam that we need to analyze in order to find the bending stiffness. The beam we needed to analyze did not have fixed supports at both ends, but instead was fixed at one end, roller at the end we want to calculate the bending stiffness, in this case node A. We then used superposition to generate the moment diagram for the indeterminate beam with the moment at A and the carryover factor times the moment at the far end. We then converted the moment diagrams to M over EI diagrams, which become the loading on our conjugate beam. So we drew our conjugate beam with the appropriate boundary conditions, applied the M over EI diagram as a distributed load on the conjugate beam and converted the distributed loads to equivalent forces over different regions. And in this case, we broke up the distributed load into 6 regions. We noted that since the slope at A is -1 radians, for the conjugate beam, the shear at A has to be -1. And the way our conjugate beam is supported, that means that the vertical reaction at A is -1. So we drew our free body diagram of the conjugate beam and applied force equilibrium to obtain our first equation and moment equilibrium to obtain our second equation. And then we solved those two equations for the two unknowns, first obtaining the carryover factor, then the bending stiffness. When we compared our calculated bending stiffness to the boundaries or range we expected from our approximation, we found that the bending stiffness KAC is within the range. When we compared our carryover factor to the carryover factor for a prismatic member, we found that they are reasonably close, and certainly the new carryover factor, or the carryover factor reflecting the non-prismatic features of this beam, is definitely within 0 and 1 as we expected. Well done.